So now we're going to take a look at buffers. So our first question is, what is a buffer anyway? So a buffer is a solution that contains two components. Those two components are either, and there we go, now try an acid and a conjugate base, or a base and its conjugate acid. So you have to have both present for something to be a buffer. Now, the reason we want both of these is because if you have an acid and base that are related to each other, what they can do is they can react with other acids or bases to control the pH of our solution. So the idea is, if I have, let's say, HF and F minus both in a solution, with HF being an acid and F minus being a conjugate base, then what happens, if I add some acid, this conjugate base F minus will react with that acid to neutralize it. On the other hand, if I add some base, the HF acid is going to react with it to neutralize it. What's important about this is what actually happens in these neutralization reactions. When the acid HF reacts to neutralize a base, it gives up a proton, so it forms F minus, which is already in our solution. Similarly, F minus, when it acts as a base, is going to gain a proton. It's going to form HF, which is already present in our solution. And what this does is it causes the pH of our solution not to change a significant amount as long as there's some of both HF and F minus present. If we run out of one of them, this quits being useful and doesn't actually act as a buffer. But as long as there's some of each of them, it can behave like a buffer. So in terms of a chemical reaction, we can think of it like this. So we'll actually just use HF. So HF plus water, aqueous liquid, is in equilibrium with F minus plus H3O plus. And so the idea would be, if we change the F minus or HF a little bit by adding some acid or base, they're going to adjust just a little bit, but the equilibrium will keep it so that the H3O plus is in about the same place. It won't be identical, it does change some, but compared to, for example, if you've worked in lab, when you work in the lab and you just add a strong acid or base to water, it changes a gigantic amount. Whereas if you have a buffer present, adding a small amount of strong acid or strong base should only change it a little bit. So buffers act to prevent there from being major changes in pH. And to help understand this, we can actually look at an mathematical relationship, an equation, that gives us this. It's called the Henderson-Hasselbalch equation. So as a reminder, this is our equation that pH equals pKa plus the log of the concentration of the base over the acid. And as a side note, remember that we can use either molarity or moles, as long as both are in the same unit. You can't have one be in molarity and one be in moles. That'll cause problems. But as long as they're both in the same unit, you can use either to do that. The second thing to remember is this is only true for buffers. You can't choose just any random acid or base. They have to be a related acid conjugate base pair. So as long as they're related, you're able to use the Henderson-Hasselbalch equation to figure out what the pH of it is. In a lot of ways, what this equation actually is if you take an ice table and you assume x is small and you solve for the different values, you can actually get to this point where you recreate the Henderson-Hasselbalch equation. So it didn't just come from nowhere. It's a simplification of ice tables if x is small. So then our follow-up question. So how does this thing change when our buffer is stressed? So the equation can actually give us some ideas on this. So our equation is pH equals pKa plus the log of base over acid. So let's say we take our buffer, like the hydrofluoric acid buffer we talked about in the last slide, and we were to add a little bit of base. So when you add the base, it reacts with the acid. And the acid forms more conjugate base. So HF is going to react with something like sodium hydroxide. It's going to lose its proton as that sodium hydroxide makes... So I need to write that down. I lost my pointer. Sorry if it's going on the screen for you. So I add some NaOH. It's going to make some OH minus because it's a strong base. My HF that's floating around, this hydrogen, is going to react with that to form water. And then we also have some F minus floating around. So since HF lost its proton, there aren't as many HF molecules anymore. Every molecule of NaOH got rid of a molecule of HF. But looking at our balanced equation, it also created a molecule of F minus. So the moles of acid went down, the moles of base went up. So therefore, this number here, our base, is going to go up. And our acid here is going to go down. But what you'll find looking at this logarithmic relationship is that it's still going to stay pretty close to the value of the pKa as long as you don't get rid of almost all of the base or almost all of the acid. As long as there's a significant amount of both, even though those numbers go up and down some, it doesn't change a huge amount. It's going to be changes like 1 or 2/10 probably. It depends on exactly how strong your buffer is and how close you are to getting rid of all of one of the substances to know exactly how much it would change. So you have to calculate it specifically. But as long as the buffer is actively functioning and you haven't run out of one, you don't expect pH changes of like 1 or 2 or 3 from only adding a small amount. Because your buffer is going to always stay within about 1 pH unit, maybe 2 pH units if you get really close to the edge of it. It's not going to change by like 3+, or else you're past the region where it works and you've gotten rid of all of either the base or the acid. Now, related to that, then, is this idea of buffering capacity and range. So, buffering capacity is just a term that tells us how much acid and base can we neutralize. So, as you have a buffer that has more that has more moles, it can neutralize more acid and base. Note that you don't just want infinite capacity because you're limited by a few things. One, practically speaking, eventually stuff just won't dissolve. You can't dissolve 100,000 grams into a little milliliter, right? We know if you take enough salt, even though we say salt dissolves in water, eventually you'll get a pool of salt that forms the bottom of your water because you wanted to make really salty water. So when you're making your buffer, eventually it just literally can't dissolve anymore. The second problem is a lot of times you actually want to adjust your buffer a little bit when you make it by adding a bit of acid or base to get it right where you want it. But if it's got a really, really large buffering capacity, when you try to change it, it's just not going to change. So we don't need infinite buffering capacity. We only need enough so that however much base or acid we plan to add shouldn't change it a whole lot. The other term we get here is range. And in general, the range that's going to work best is plus or minus 1 of the pKa of your acid or base you're working, or the acid you're working with. So for example, if I want to buffer at a pH of 4, I'm going to want to pick one that has a pKa somewhere between 3 and 5, and as I get closer to 4, it's going to work better. That's because our buffer works best when the base and acid ratio is equal. And in general, we want our ratio to be somewhere between 1 to 10 and 10 to 1 as the highest extremes. You never want more than 10 times of one component or the other, and even at that extreme, it starts not to function so well. You really want to get closer to 1 to 1, but you can go outside of that because you have to practically work with what buffers you have available. So, this is our answer to our question, how do I choose a buffer? Is I pick the buffer that would have a pKa closest to my pH that I'm going to want to work with. That'll help out with picking a good buffer. So now let's actually do a numeric problem with this where we figure out some pHs. So I suggest here that you pause my video, give this a try for your review, and then afterwards see how I do it, especially if there's any steps you get stuck on. Okay, so let's work this. I'll also set aside that if you can't do A, or let's say you had trouble with A, B, or C. Let's say you had trouble with all of it. After I do A, see if you can go on and do the others. But especially, even if you can't do that, if after I do B, C is very similar. I would strongly encourage you to try C after B if you had trouble and you were just like, I can't do any of this, or I can't do B and C. Having said that, let's start with A. It is the most straightforward. We have a buffer. Since we have a buffer, we can use the Henderson-Hasselbalch equation to get it. We have pH equals pKa plus the log of the base over the acid. So in this case, we're told the Ka, so we need to find the pKa. So pKa, remember this P stands for the negative log of stuff, whatever you're doing the P of. So negative log of 3.5 times 10 to the negative fourth is going to give you a pKa of 3.46. So our pH is going to equal 3.46 plus the log of 0.150 over 0.200. We do that, we'll get a pH of 3.34, and that's our answer to A. Now, let's take a look at B and C. B and C are going to be a bit more work than that, but it's still very doable. So here, we're going to start with B, where we're going to add 0.100 moles of HCl. So that means, first we want to point out that HCl is a strong acid. Therefore, whatever concentration of this we add, what we're really adding that we care about is HCO+. And their concentrations are going to be equivalent because every molecule of HCl you add turns into a molecule of HCO+. So whatever the molarity of HCl was, it'll also be the molarity for HCO+, or more importantly, we're going to do this in moles. So find moles. The reason we're going to do this is because with our buffers, we tend to work with this because this is what's actually going to help us figure out how much our acid or base changed, because we can't just add or subtract molarities to do this. So we're going to work with this in moles. So, sorry, I shouldn't have these little concentration brackets here, because we're going to work with this in moles. So every molecule of HCl you add is going to turn into a molecule of HCl+. Now, the second thing we need to figure out is what equation matters. Well, you're adding an acid. Acids react with bases. So in our buffer, the HF is the acidic part. So that part is going to be one of our products. Our HCl isn't going to react with HF. On the other hand, our NaF, remember, turns into Na+ and F-. From our work with salts, we know the sodium is a neutral salt. It doesn't do anything. We're not worried about it. But our F- here, that's our conjugate base. So that's the base that's going to react with our acid. So we need to come up with our chemical equation, which is F- plus H3O+. These are both aqueous. They're going to react to form HF. So again, we're reforming the acid that's present, which should always happen, plus water. Since the H3O+ gave up a proton, it's now just H2O. So for this, since we're mixing these two together, we're going to use a BAA table is how we've been doing this. So our before, well, I don't know the moles yet. Remember, ice tables are the ones in molarities. Our BAAs are the one in moles. So to do this, I need to figure out, well, I had 0.2 molar and I had 1 liter. So if I take the volume and multiply it with the molarity, my volumes will cancel and I'll be left with moles. So in a 1 liter solution, I would have 0.2 molar. As an aside, you do have to pay attention to the volume. If you'd only had half a liter of buffer, then you would have had only 0.1 moles. So you still have to make that conversion. So try not to ignore that part in case you don't work with exactly 1 liter of buffer every time. So my 1 liter of HF contained 0.200 moles of HF. Liters canceled. I've got 0.200 moles. We can do the same calculation with my F- and my NaF, and I'm going to get 0.150 moles. So my before, I start with 0.200. My H3O+ I'm going to treat as approximately 0. My HF, I have 0.150, and we're not worried about the water the whole way through. So what am I going to add? I'm adding acid. I'm adding 0.0100 moles of this. No A-, no HF. So now we think of it kind of like we did in 1211. We're not going to have a base and a strong acid coexist. One of them is going to be gotten rid of. So we didn't add as much acid as we had base. That means that our H3O+ is all going to get neutralized by the base. So we're going to lose all of these molecules we added. So we're also going to lose that much F-, since every molecule of H3O+ we want to get rid of also gets rid of an F-. When we do that, there's a 1-to-1 relationship between the H3O+ and the HF. That means we're going to add 0.0100 over here. And then we're not worried about the water. So, I did not mean to make that zoom in. Sorry about that. This is supposed to be an A. There's a little menu this brings up I can't avoid, so I'm going to try to be careful about that. So we subtract 0.2 minus that, and we'll get 0.190 moles. We don't have any extra H2O+. We've got 0.160 moles of HF. So now we can plug these back into our Henderson-Hasselbalch equation that pH equals pKa plus the log of the base over the acid. So we have a pKa of 3.46 plus a log. As a reminder, when we talk about Henderson-Hasselbalch, we can use moles or molarity as long as we use them the same. So we're going to use moles for each of these. Our base is F-, so that'll be 0.190. Trying to decide how to fix this the best, because obviously I put these numbers in the wrong places, and we can see that because my F- is clearly wrong and my HF is. So I've got to fix a bunch of numbers. I do not have time to re-record this whole video. I'll make a note about it on Courstin. I apologize for these numbers being wrong. I'll make a big warning so everybody knows before looking at this. So hopefully, if you're listening to this, you saw my warning on our message board that I did those backwards. But at least I noticed it before finishing and something felt off. So my F- should be 0.150 because that's how much sodium fluoride I had. So when we subtract it, we'll get 0.140. And over here, when we took 0.200 and added something, we get 0.210. Now, our log of our base is equal to 0.140 divided by 0.210. So our pH equals 3.46 plus the log. Let's do that. log of 0.14 divided by 0.21. So that's going to give us 3.46 plus that. Yes, we will get our pH. My cursor disappeared on me again. There we go. pH equals 3.28. So there's our pH. So that'll be for part B. And this is actually where I started to notice the problem. I was doing a check in my head, and I was looking at what the value was going to come out. I thought pH was about to go up when we added an acid, which didn't make any sense. So this answer is logical. Our pH went down. It was 3.34. We added some acid, it went down to 3.28, which is what we would expect. If you had put the numbers in reverse, like I was about to, you would have got a number higher than 3.34, and that has to be wrong. So that's how I noticed my mistake and how I was able to fix it before finishing up the problem. Now, let's clear all this out so we can do C. I also suggest you try to do C on your own first if you haven't done so yet, because it's very similar to B. You just have to figure out what the NaOH is going to react with and what equation matters there. So first part we want to pay attention to is NaOH is going to give us a bunch of OH minus, specifically 0.0100 moles of it. So that means since we're adding a base, it's going to react with the acid portion. So we have HF plus our hydroxide is going to react to form F minus, because it's going to take one of those protons away from HF, and it's going to form water. So our before statement is we started with our HF was 0.200. Wait, let's make sure I do this. Yes, because now we've switched which sides everything is on. Now I see what my mistake was earlier. I didn't switch sides earlier. We're starting at approximately no hydroxide. We've got 0.150 moles of our F minus. We're not worried about the water. So our addition is we're going to add 0.0100 moles of this. No F minus, no HF. So we're using up some of our acid. We're going to lose all our strong base, and we're going to gain some F minus. Because again, every molecule of HF that reacts with a base loses one hydrogen. When it loses a hydrogen, it forms F minus. So every HF we got rid of has to form a new F minus molecule. So then after we do all that, we'll get 0.190, we'll get 0 here, we'll get 0.160 here. So now we have the pH equals the pKa, which is 3.46, plus the log of the base over the acid. Now the base this time has changed sides. It's the F minus, so that'll be 0.16 on top, and that'll be 0.19 on bottom. So we plug all that in, and we'll get a pH of 3.39, which is higher than the pH of 3.34 we had for the initial buffer, which is going in the right direction. So that's how you do a buffer problem, minus the mistakes I made on B. If you don't make those, it makes the problem a bit easier to do.